In this video, we're going to take a look at inverses. So we know what a relation is. It's just a set of ordered pairs. It's showing me how two sets of data are connected. The inverse of the relation is the reverse of that. It undoes the original process. So instead of xy, we're going to flip it and have yx. So if I have a set of ordered pairs as my relation, then I would find the inverse simply by flipping every single one of those ordered pairs. So instead of 3, 1, my inverse will have 1, 3. Instead of -2, 4, I would have 4, -2, and so on. That's all there is to coming up with the inverse. It gets a little more complicated if we have a equation. So let's look at y equals x squared. We know that's the parabola. I'm going to go ahead here and I made a chart for different x values and y values for my parabola. I've got -2, 4, -1, 1, etc. And I can graph that here. Okay, so there's my parabola. We just said that the inverse is going to flip all those x's and y's. So in this green chart, I took every one of those ordered pairs and I flipped them. So what was the x becomes the y, what was y becomes the x. And we're going to graph those. So 4, -2 would be down here, 1, -1, 0, 0, etc. It's kind of interesting that the shape of the graph is actually very similar to the shape of the original function. That's not a coincidence. There is a relationship even further than that. You see I've drawn a red line here. That is the line y equals x. If we were to pick up the picture and fold it on that diagonal line, we would realize that those two pictures align with one another. So it's important to note that the graphs of inverses are actually reflections over the line y equals x, that diagonal line through the origin. Something else to note is that although y equals x squared is a function, its inverse is not, because it would fail the vertical line test. Okay, so the rule is that if you have a function that's 1-to-1, it will have an inverse that is a function. If it's not 1-to-1, its inverse won't be a function. All right, so here I have f in blue, and I want to find its inverse. All I would have to do is identify the ordered pairs and flip those. So instead of -5, 0, I would have 0, -5. Instead of 3, 4, we'd have 4, 3. And instead of 4, 6, we'd have 6, 4. Connect the dots. They're still linear little segments. And then if I draw in that diagonal, this time I put it in green, and I imagine picking up the graph and folding it, I can see how those two would line up with one another. We can also talk about finding the inverse from an actual formula. So f of x is my function. The notation for the inverse is f to the -1. We don't say f to the -1. We say f inverse of x. Okay, so just get used to the new notation. Finding that inverse is actually a pretty straightforward process. You're going to replace your f of x with y because it's easier in the equation. And then, because we're talking about inverses, we're going to swap all the x's and y's. Hardest part is step 3. We actually have to solve for y. So it's going to involve a little bit of algebra there. And then finally, when we have y by itself, we're going to use the new fancy notation and call it f inverse of x. Let's take a look at an example. If I have a 1-to-1 function, and again, why do I want to start with a 1-to-1 function? Because its inverse will also be a function. Then, and I want to find its inverse. So f of x is equal to 3x plus 2. First thing I did is swapped out f of x for y, and then I switched the x's and y's, and then I say, okay, I want to solve for this y. So we'll subtract 2, divide by 3, boom, I have my f inverse. Now I could graph these two in a calculator and verify. So let me show you that real quickly. If I turn on my calculator and I clear out there, I put in my first one, 3x plus 2. And then I put in my second one. So I want the calculator to understand everything on the top is going to get divided. So I have it in parentheses. And I'm going to look at the standard window. I do have to recall that my window here is a little skewed because it's a rectangular window. But if I imagine drawing a diagonal line through here, I can see that those two would look like they're going to line up with one another. So that gives me confidence that I solved correctly. Another way you could do it is if you put a 2 into f of x, let's say 2 times 3, 6, 8, right? Now if I took that 8 and put it down here in the inverse, do I get back my 2? Well, 8 minus 2 is 6. 6 divided by 3 is 2. So if you put a number in f of x, take your answer and put it in its inverse and get back what you started with, that tells you you're also on the right track. All right, one last quick a couple examples here. If you have f of x is equal to 7 minus x cubed and you want to find the inverse, same process. Replace f of x with y, swap the x's and y's, and then solve for the y. The only trickier part in this one is you're solving for y and you have a cube, so you have to remember to take the cube root. Again, I've shown you a picture here of what the original function and what I found for the inverse look like, and they do look like they align across that diagonal line. Fractions can be a little bit trickier for some, so let's go through this one. If f of x is equal to 7 over x minus 2, same steps, f of x becomes y, switch the x's and y's. Now we're trying to solve for this y down here. We have a fraction, so we want to get rid of it. The key to getting rid of fractions is by multiplying by the common denominator, in this case the whole quantity of y minus 2. So I multiply on the right and it cancels the denominator. On the left I get this expression. Now I could distribute that, or I could just say I'm eventually going to solve for y, so let's get rid of this x. So I divided both sides by x, and the last step would be to get y by itself by adding 2. So I come up with this final answer for my inverse. Let me know if you have any questions.